All right, the session is now recording. So, welcome everyone to the fifth weekly discussion session for the NPTEL course titled Physics of Nanoscale Devices. As always, my name is Jyotishwaran. I'm a PhD student from the Department of Electronics and Communication Engineering at IIT Roorkee. So, moving on to the topics today. As mentioned last week, our in fact, our singular topic of discussion today is going to be the notion of modes in a ballistic channel. So, while discussing the idea of modes, I'll also kind of go through the idea of what ballistic channels are. Okay. So, and then we can go through the various concepts associated with modes. We'll solve some problems to illustrate and elucidate the concepts along the way. And we will end with the generalization to the diffusive limit. So, to begin, this idea of a ballistic channel. Now, this is a semi-classical treatment. So, classical treatment. And to be more precise, it's a semi-classical treatment of a quantum phenomena. Because at this point, someone can ask me, what about, the normal model of conduction that we know in semiconductors? Because there also we invoke the concept of conduction band, valence band, there are band gaps, and these are purely quantum mechanical concepts. So we are also in invoking quantum mechanics there, and why is that not a semi-classical treatment? The answer is yes, of course, that is a semi-classical treatment, but that is a semi-classical treatment to explain a classical phenomena. That is the behavior of diodes and conventional BJTs and MOSFETs and so on and so forth. But here, what we are doing is the device that we are considering, nanoscale devices, by virtue of their size, will inherently display quantum properties. So we are now using a semi-classical treatment to explain what the quantum properties of the devices, the device is. We are not looking at multiple devices. We are devices. We are just looking at one. And when we talk about the diffusive limit, this is essentially the macroscopic conduction, because the idea of conductors and insulators itself is quantum mechanical. Like, to explain them fully, we cannot do so without the aid of quantum mechanics, without the invoking the principles of quantum mechanics. So I cannot say this is what classical conduction is. This is the macroscopic conduction that was observed in the early 18th century, and eventually led to Maxwell's equations and all those things. So this is the macroscopic conduction limit. Okay. So to begin with, we'll start with the current flowing through a ballistic channel. So that is given by this expression, 2q upon h into gamma of e times pi times d of e by 2, which is the density of states, times f1 of e minus f2 of e dE. So this is the differential current, the integrand, and we are integrating it over all, rather than differential current, I should say is the specific current, and we integrate it over all energies to get the total current. So just a reminder, the kind of structures that we are studying are two-terminal devices. In fact, I think all the way until week, I don't know, 7 or 8, we'll be only looking at these kinds of devices. So we have two bulk terminals, and this figure is of course not to scale. So please don't think the channel is this much longer than the terminals. This is just for purposes of detail. So we have a nanoscale channel, and and you have bulk contacts. Okay, so we know this to be the current expression, the derivation you must have followed through the lectures. Additionally, I also asked you to practice it during the tutorials. If there are any doubts, feel free to either ask during the session or post a question on the forums. So now, what does this imply? What does this expression tell us? So we can see this has three distinct parts. I have this, and then of course I'm like bunching up the constants as well. I hope everybody understands that the constant terms are just what they are. Like they are just multiplicative factors. So I have three terms here. So let me say this is 1, 2, and 3. So first things first, or rather, in this case, the first is going to be the last because that's what we shall be discussing. And 3. So the one that we can be most sure about is the second one. This tells us the density of states. So what are the density of states? Density of states essentially gives us the number of energy states per unit energy or at a given density of energy states at a given energy value in a unit volume of the system. So this is per energy per volume. So that is the units of these things. So it is inverse of energy and inverse of volume in the appropriate dimensions. And the last quantity, we shall see why this is the case. This essentially tells us the probability of finding conduction electrons. Now, why this is the case, we will see in just a minute. Okay, and the first quantity, essentially gamma of E, that is what we refer to as moles. Now, if you have followed the derivation, you will know that gamma of E is nothing but, I shouldn't say it is nothing but, previously the term here would have been like for the equilibrium current. Let me quickly write it down here. So while deriving the current, we will have this kind of a relation. N1 of E minus N2 of E by tau is equal to dN by dt. So we would have had this kind of, this is the current. So here the 1 and 2 refer to the contacts. Yeah, so I should be more precise about that. In fact, let me avoid further ambiguity by doing the following. So let me say this is B, this is B, A, O, C and C, and A. So there are three parts, A, B, and C instead of 1, 2, and 3. And I'll go up here and write this to be region 1 and region 2 so that there are no notational clashes. So this is the current. In fact, I can simply say instead of current at equilibrium, because equilibrium may refer to a static condition. So this is the steady state current. essentially this quantity integrated over dE is the steady state current. Now from here we can write the N as d into F, and the 1 by tau quantity, which is the transit time for an electron of a given energy through the channel, is what we replace by the energy broadening. So we write like this. Yeah, gamma of E. So using the energy time uncertainty principle, I can say tau of E times gamma of E is of the order h bar, and from this we get 1 over tau of E is equal to gamma of E divided by h bar, which is, sorry, h bar. This will give me gamma of E into by h into 2 pi. And after that, the factors are kind of rearranged and we will get the net current. The reason why we are holding 2q by h out here is under certain special conditions, which you may have already seen in this week's lecture. This quantity right here will also become something important. After certain approximations are done, this quantity here will also become somewhat important. So yes, so this is where we get that. And now this quantity M of E, which we essentially, so what we do is the following. We will combine A into, okay, I should not have said A is the modes, I'm sorry. A is the energy broadening. Okay, so yes, now I can write the final statement. M of E essentially is the combination of these two. Okay, so it is the combination of A and B. So I shall write that somewhere up here. I shall say M of E is A times B. So now what does this mean? Now we know that D of E gives me the number of energy states at a given, like essentially the density of energy states at a given energy value per unit volume of the system. And gamma of E is giving me something called energy broadening. Roughly, what does energy broadening stand for? When we have an electron move through the channel with a particular energy level, then we can be assured that, okay, let me start a new slide and kind of explain it over there. So essentially, we are starting now. Let us just look at the channel. So we shall briefly look at energy broadening. So when I'm considering the channel like this, or I think I should relax myself. Let me draw a slightly bigger version of the channel. Let me say I'm calling this what? why am I struggling so much to just draw a straightish line? Yes, somewhat better. Okay, so I have my contact 1 on this side, then I have my contact 2 on this side. So one thing that you may have learned from the previous week's uh, lectures is that these two interfaces, this is where energy loss or gain occurs. In fact, it's almost always energy loss, and that is what gives us the idea of resistance. Like, although we are calling this as ballistic transport, so what does ballistic mean? Ballistic means without collision. Without collision or scattering. So in the channel, the electron will not lose energy. When an electron enters this channel, it maintains the same energy through and through all the way till it reaches the second contact. So there is energy loss over here and energy loss over here. Loss over here. So typically, if I'm looking at the energy diagrams, it starts at some energy level E1, loses some energy, enters the channel energy level EC, and will then lose a little bit more energy and then enter the energy level E2 on the second electrode. So this is second terminal. So this is how the electron moves. Now it is at energy EC for the entire duration. It is inside this channel because our transport is ballistic. Therefore, and I know the electron is definitely moving from contact 1 to contact 2, which implies the time spent in here, essentially whatever energies my electrons are entering, which will of course determine the velocities that they have. When they reach here, they will spend a time tau, which is of course defined by the energy, because energy determines the velocity, and therefore instead of writing tau as a function of velocity, I can write it as a function of the energy itself. Tau of E is the lifetime in the channel. And from this, we will invoke the uncertainty relation and then say tau of E is equal to h bar upon gamma of E. And from there, we shall write 1 upon tau of E is equal to gamma of E by h. Again, this is an approximation because typically when I'm writing the uncertainty relation, this is of the order. This is not an exact equality. But for our present purposes, we can make this assumption. It is fine. It is perfectly fine. Now, what will this do to my energy level? So what happens because of energy broadening? What essentially happens is the following. I hope this works. So, am I? Oh yeah, I'm smudging over it. I should be doing that. Is there any way I can? The highlighter work? It should. Slightly lesser thickness. Brilliant. Yes. This is exactly what I wanted. So I, when we have an electron moving through the channel, the single energy level EC, which is how energy levels are present in solids, they are like quantized energy levels, will get smudged over. So this smearing out of the energy level, this is given by gamma of E. And as you can imagine, gamma of E is going to be very small, because tau is, whatever time the electron takes to cross a channel, which is a few nanometers in length. So even if I assume a very modest velocity, this is going to be a very small time. Like the time taken is not going to be too large. In fact, even if I assume the electron is traveling at, say, something like uh, half a meter per second, then even in that case, the electron is going to cross this channel in a matter of nanoseconds. So gamma of E, if that is nanoseconds, is 10 to the power minus 9. To get 10 to the power minus 24, I will need gamma of E to be 10 to the power minus 25, which is micro electron volts. So this energy broadening is not going to be very large. It is not like I'm going to have overlapping energy levels. We are but going to have only a very small broadening in energy. So if my channel has multiple energy levels, essentially if I have several energy levels like this in my channel, depending on the density of states in the channel, then upon, so let me call these EC1, EC2, EC3, and EC4. Then upon moving through the channel, each energy level will get broadened by a certain amount. Now, that need not be the same amount for every energy level. In fact, almost invariably, it is going to be different, which is why I'm kind of, drawing them to be slightly different from each other. And I'm also not indicating a trend that as energy decreases, the broadening will. In fact, as the energy decreases, the broadening, as you can imagine, because if the energy goes down, then the velocity will go down, then transit time will increase. If transit time increases, then the broadening has to come down because that product is a constant. So that much we can say with reasonable certainty, that as the energy decreases, the energy broadening will decrease. So I've verbally explained it, but I hope if I just write this statement here, people can infer it on their own. Okay, so this is kind of like, if you are unable to figure this out, please practice this as a homework question. Why not? Okay, so this is the idea of energy broadening. Now, what do I mean by modes? So remember that while in the channel, the electron cannot gain energy, because it cannot gain or lose energy because the transport is ballistic, which implies the electron cannot move from one energy level to another. Therefore, when we are inside the channel, only those energy levels will be chosen whose like broadening does not cross over into another energy level. I hope you can see that, because let me say I take a very high energy level where the broadening will be very large. Then that may broaden and include all other energy levels also. That implies that particular electron is equally likely to be found in any of the energy levels that is present within gamma. Because this gamma of E is essentially what? It is the uncertainty. This is the uncertainty in energy. And to, if you want to recall more about this uncertainty, please go back to week one's discussion sessions or any of the lectures in week one, where although this uncertainty is sometimes treated statistically, it is not a statistical quantity, it's actually a very physical quantity. So, and I don't want this uncertainty to become so large that multiple levels get enveloped in it. So ideally I will want my broadening to be something like this. I will want essentially non-overlapping energy broadening profiles, and that restricts the number of energy levels that are available for conduction in the channel. So d of e gives me the number of energy states present in the neighborhood of an energy level, and this broadening tells me how much they are stretching by. The product of these two will tell me how many available energy levels are present. So from that we come to the definition, the proper definition of modes, which modes in a ballistic channel. So we denote this by M of E, or rather, this is the mode density function. So let me be more clear. M of E is number of modes at a given energy value. Now, just a brief comment here. Whenever we write functions such as tau of E or M of E, I am treating the energy there as a scalar. It's just a number. The E here does not refer to the electronic energy levels in the solid or the channel, which will be discrete quantities. Those are energy states. Of course, the energy states are defined by their energy values, but when I write just E without referring to an energy state, I'm just talking about a number. So it is, so this E can vary continuously. This does not mean the system has continuous energy values. Okay. E, let me quickly write a side note here because I used to have this confusion when I was studying these things because people write D of E and they plot a continuous graph. And I'm like, why is that? Because I mean, I know the energies are discrete, so why am I not considering discrete energy levels in the solid while representing the density of states? Well, the answer is when we are writing these density functions, we are assuming a continuous energy spectrum because these graphs are smoother and better represented when we are considering an energy continuum. And even if we go to the discrete limit, the profile is pretty much going to be the same as we shall see further down the course when we shall try to do a more accurate representation of say 2D density of states or 1D density of states. You will see that it is indeed like essentially treating energy as a continuum gave us the right idea all along. Okay, so let me quickly make a side note here. E given here is a scalar and has continuous values. I mean, that should also be apparent from the fact that I am integrating for the current here. I mean, if they were discrete values, I would have just written this as a sigma summation. But this is an integration for this very reason. Okay, so yeah, end of the side remark at a given energy value. So what I shall refer to this as the mode density function. Once again, this is a density function. So one should not think that these are the actual number of modes available at an energy. In fact, the number of modes that we have is more precisely given by this quantity. M of E dE will give me from E1 to E2 will give me the number of modes available between E2 and E1. So this is the standard rule. So the number of modes is given by this integral. Now number of modes multiplied by the probability of finding the electrons in those modes will tell me conduction is occurring because any electron present in the channel like above the equilibrium energy level, which we shall see what it is going to take part in conduction. So those are the energy levels that I shall be interested in this integration and in this integration over here. And therefore, integral E1 to E2, M of E f of e d should give me an idea of the number of electrons taking part in conduction. Now the dimensions and exact scaling values will change. I will come to that maybe in the next week. For now, understand that this is the spirit of it. This is a density function and not a probability density function, mind you, because those need to be integrated to 1. F of e is a probability density function as discussed before, but m of e has no such limits. So taking part in conduction in the channel or through the channel. Wonderful. Now let us move to the first problem for the day. So show that this quantity f1 of e minus f2 of e is indeed the probability of finding a conduction electron at energy level E inside the channel. So how shall we go about this? Let us go about this by considering two cases. So first, let me take case A, which is the equilibrium case. So at equilibrium, V2 minus V1 is 0. No voltage is applied across the two terminals. And as a result, I is also equal to 0. So now, again, this is a concept that was invoked during the solution for the stored charge capacity of the channel, stored charge density of a channel. So at equilibrium, there is one thing that we definitely know, that the Fermi levels of the devices, of the three components of the device, are going to be aligned. So let me say this is the Fermi level EF, and I will have my source or contact 1, as I'm calling it right now. We shall not go into source and drains yet. And then we have contact number 2 over here with the same Fermi level. So, and then we will have the channel. So I will also use red to highlight the channel because I have use for the blue sketch. Okay. Now since this is the Fermi level, at any given temperature, I can do the following. I can essentially sketch the Fermi distribution. So if I take this point to be 1, and this to be half, then the Fermi distribution is going to be something like this. It cuts at half. Did I make this a continuous line? Yes, I did. So it's something. Yes, drawing this thing straight is a difficult task. Drawing this sideways is downright impossible for me. And similarly, I can say, okay, I have another energy axis over here and another Fermi level over here. And this is the halfway point. This is 1. So we are assuming they are the similar materials on both sides. So the Fermi level is going to be slightly smoother. Can I do that? Yes, hopefully. Yes. Yeah, I hope people can understand this. So I have the same Fermi level. Now, remember this previous picture. Conduction will always occur like this. It will start from an E1, go to EC, and then go to E2. Now, that essentially means I am starting at a very high, not very high, at a relatively higher energy level here. And we also know for a fact that conduction electrons are typically found above the Fermi level. Because below the Fermi level, those are the electrons that, at least in our conventional definition of semiconductors, below the Fermi level lies the valence band. And valence band electrons do not participate in conduction. So I will be looking for some energy level E over here. And that conduction electron remains a conduction electron that when it comes to side 2 as well, to terminal 2 as well. So I have terminal 1 and terminal 2. This is the channel, which implies I will need an electron level. Just 1 second, please. Yeah, apologies for the interruption. Yeah, as I was saying, yes. So essentially, I will need one state. I will need to find a state with an electron here. And correspondingly, I will need to find a state with empty electrons, like without electrons here, so that the electron can enter this channel, move through this channel, and jump out of the channel. So in that case, what is going to be like, what I'm trying to say here is, now as you can see, the Fermi levels are aligned because the system is in equilibrium and no current is flowing. And we will also know that the value of the Fermi function essentially to the left of the for most reasonable temperatures. In fact, if I go to very high temperatures, this is going to be a flat line at half. But even at something like 300 Kelvin, where kBT is a very small value, it is not high enough to populate the entire valence band, sorry, conduction band, because we know the intrinsic charge carrier in even materials like silicon is going to be something like 10 to the power 10 electrons per centimeter cube, which is actually pretty less. So even at room temperatures, silicon is going to behave more or less like an insulator. It is a semiconductor, yes, but it's going to be a semiconductor with a very high resistance. So the probability of finding conduction electrons in the terminal 1 is very low, terminal 2 is very low, and thereby it is also very low in the channel. Therefore, at equilibrium, and since both the Fermi levels are aligned, F1 of E minus F2 of E is going to be 0. Even if there are minor differences between the two materials, I can say that it's going to be 0, which will imply no conduction occurs. Now, moving to the oops, here we are. Yes. Now moving to case B, which is the non-equilibrium mode. Or non-equilibrium condition. I should be reusing the word modes. So almost the same situation. Let me say I have terminal 1 and I have terminal 2, and let me say V2 minus V1 is greater than 0. Yes. So now one thing we can say about the Fermi level is whichever terminal has the higher voltage, there will be a further lowering of the energy level because the electrons are negatively charged. So the actual change in energy is going to be Q times that. So minus Q times that, because Q times that, and Q is a negative value. So the change in energy is going to lower the Fermi level on the higher voltage side. The current flows from high voltage to low voltage, but the electron movement is in the opposite direction. That's the long and short of what I'm trying to say. Okay. So in this case, I will need two lines. So I will say I have my first line over here. And let me say this is the Fermi level of the first material. So this is EF1, EF1. And then I will draw a second line, again just for representational purposes. Going to be here. Call this EF2, EF2 on this side as well. Now, and of course I have my channel connecting these two materials, these two contacts. Now how is the Fermi level going to look like? So, or rather the Fermi distribution going to look like? This is going to be something like this over here, 1.5, and then on the second electrode, my Fermi distribution is going to be more along this line. Although it's not going to be so drastic, so this is just exaggerated for extra effect, and also because my drawing is kind of sloppy. But nonetheless, this gets my argument across. So what is happening here? What is happening here is there is now a significant number. So between, what is the observation? So essentially, if I'm looking in this region here, if I'm looking in this region right here, then what are we finding? So of course here I is not equal to 0. I will not call I positive or negative. So in this yellow region, we have many occupied states in terminal, occupied electron states in terminal 1. Between EF2 and EF1. Many empty states. Likewise for material 2 between EF2 and EF1. So like higher value of the Fermi function means higher probability of finding electrons, lower probability of finding electrons. For conduction to occur, what do I need? I need this kind of a setup. I will need some E1 to an EC to an E2. So I will need the probability of one of the states at value E1 being occupied here and the probability of one of the states E2 being empty here. So for conduction, E1 should be occupied in terminal 1 and E2 should be empty in terminal 2. So what is the probability of this event occurring? These are two independent events, so I can just directly multiply their probabilities to get this total probability. So this is going to be f of E1 because that is the probability of finding an electron at energy E1, essentially probability density, and this should be empty. So the energy is going to be 1 minus F2 of E, which implies the net probability. The definitions of this page is, of course, why not? So this is going to be f of E1 minus F1 of, oh, not f of E1. Just one second. What is the notation that I have used here? It is F1 of E. So I should say F1 of E1 and F2 of E2. Yes. So this is F1 of E1 times F1 of F1 of just one second. Yes. F1 of E1 minus, sorry, not minus, multiplied by F2 of E2. Now I will make a very strange kind of an approximation, but it will make more sense as we go further. Maybe in the next week, this approximation will make far more sense. The thing is, since EF1 is significantly above EF2, and I know below the Fermi level, my Fermi function is almost 1 for a very high value. So in this region, I can assume F1 of E1 to be 1 because I can take E1 to be at any point over here, very close to the Fermi level because, okay, yeah, I'll put the reasoning this way. The conduction always occurs at electronic levels very close to the Fermi level. So over here also, I will look for an electronic energy level that is empty very close to E. And here I will look for an electronic Fermi level very close to EF1, where the value of the Fermi function is bound to be very close to 1 when compared to that on side 2. So over here, I will just say this quantity is approximately equal to 1, and therefore this is equal to F1 of E minus F2 of E, essentially equivalent to. So this gives me the probability that an electron at energy E is available for conduction. And that is essentially what we have in this expression over here. Okay, so that gives us the answer to problem 1. Now let us look at modes in a ballistic channel. To be more precise, we shall be focusing on a 2D channel, and this is pretty much this is going to be our entire discussion for the next. I mean, we will also briefly look at a couple of things. Wait. Oh, sorry. No. Before we reach the diffusive limit, I'm sorry, I forgot what I was supposed to cover in this session for a brief moment. So yeah, but a good amount of time is going to be spent on this quantity right here. Now, I hope you can follow the derivations from the lectures. Right now, what I'm going to do is I'll just say I'll take this expression for granted. If you need any more explanations on what this expression is, then I will recommend that you go back and go through the derivations. Or if you have any doubts, feel free to ask right now. Uh, yes. So the mode density function in a 2D channel is given by this expression. W times H by 4 into Vx plus of E average expectation value of Vx plus of E times d2d of E. So this Vx plus of E is the following quantity. It is the average velocity in the positive x direction. Now, why am I considered only about the positive x direction? Because when I'm talking about a 2D channel, I'm considering a 2D structure like this, a sheet, where this axis is the y-axis and conduction is occurring along the x-axis. Okay, and I have conduction happening in this direction. For such a system, for such a 2D channel, a two-dimensional channel, yes, the quantity that apparently determines the modes is this, which kind of makes sense because ultimately, what did I want? I wanted a quantity that was reciprocal of, going all the way back up here, I wanted a quantity that was reciprocal of the transit time, tau. Now, reciprocal of the transit time is going to give me something like the velocity. It just makes sense because, oh, sorry, apologies. Yeah, in fact, yeah, I'll come to that in just a minute. So this is the thing here. And now this quantity, of course, it has connection to the de Broglie wavelength or the de Broglie wavelength of an electron. So what is lambda dB of an electron? That is equal to the Planck constant h divided by the momentum p. For non-relativistic cases, p is mass of the electron times the. I should be very careful in writing here because I have already used V for voltage. Yeah, lowercase v. Whenever I use uppercase V, it is the voltage, lowercase v is the velocity. And another result that I am taking for granted, although this cannot be derived, is the energy dependence that the density, the mode density function has with E can be given as e to the power 0.5 plus d, where d can be minus 0.5, 0 and 0.5 for a 1D channel, 2D channel, and a 3D channels respectively. So essentially, just like we had the energy dependence for the density of states, which was minus half, 0 and sorry, yes, minus half, 0 and uh, wait, was it minus half? No, it was not minus half. It was half, 0 and 3 half. No, it was minus half. Oh my god, I'm sorry. Let me just write it before I get any more confused. So d of e is proportional to e to the power minus half is proportional to e to the power 0 and e to the power 3 half for a 1D, 2D and a 3D channel. And if I'm looking at m of e, then that is proportional to e to the power 0, e to the power half, and e to the power 1 for again a 1D, 2D, and 3D respectively. Oh, this is not 3 by half, this is 1 by half. Apologies. Yeah, minus half, 0, and half, and this is kind of shifted by a half. So this is 0, half, and 1 over here. Okay, so yes. Now the second problem is derive the relation between m2d of E and the de Broglie wavelength lambda b. Why did I say lambda b? It should say lambda dB. Yes. So what is this going to be? So let us start with the definition of the number of modes. M2d of E is W into h by 4 to average velocity Vx plus of E d to d of E. Now, what is d to d of E? I know d to d of E for a 2D material is going to be per unit area. Now, okay, I should also clarify that this quantity here, d of E, is defined per unit area. Okay, so this is per unit area. Now, when I write d2d of E, d1d of E, and d3d of E, this is for a particular 2D system. 2D system. So over here, what I will have is this quantity h bar squared, which is the density of states for a 2D system, multiplied by area of the channel. So A, where A is equal to L into W. So this is the area of the channel. Okay, so first I will substitute that. So this is going to be, oh no, did I make a mistake here? Or did I not? Is this going to be multiplied by the area, or is this going to be, oh yeah, no, but even then, I have made a mistake. It is the other way around. This is per unit area, and this is just like, you know what, just forget this for a second. It will become clear in just a moment. So the total density of states is going to be this quantity multiplied by the area, but d2d of E is given to be this. Oh yes. Now I need it per unit area, so it has to be divided by the area. Yes, into 1 by A. It's not, yes, now I can see this. That was the mistake I was making. It's not multiplied by the area. So this will be, and of course for a 2D system, it does not depend on the energy level. So this is density of states for a particular system. Okay, so yes, so this is going to be h by 4, not 9, as it may look here, into m times Vx plus of E into pi h bar squared 1 by A. Should there be any, shouldn't there? Oh no, I have written extra m over here. No m over here. Just give me 1 second. Yeah, apologies for the intrusion. I just wanted to check something just to be sure what I had said previously was the right thing to do. Forget this for now. Okay, there is no L appearing in this picture yet. Okay, so now what is this quantity Vx plus of E? Now the derivation for this was done in detail during the lectures. So I recommend that you go back and read through that. The idea is when I have a 2D channel, ballistic, semi-classically when I look at an electron, it can have a velocity, any electron moving from 1 to 2 can have a velocity varying like this. So I will just take the angle here and essentially integrate over this to find the average velocity. Here I will assume that the electron can have uniform, like the velocity is very uniformly with the angle theta. So average Vx plus of E is going to be integral. So the angle can vary from 0 to pi. Just one more second. Yeah, I'm sorry for pausing and resuming the session over and over again. The thing is, I have a slight cold, and I don't want to sneeze into the camera or the mic because I already did that once. So I don't want to repeat that because I know that it can be quite annoying. So V cos theta d theta divided by integral 0 to pi d theta. So this will give us, I'm not solving this integral. In fact, it's pretty straightforward to solve because at a particular energy, this V is constant. So it's going to be integral 0 to pi cos theta by d theta. So this is going to be an integral of minus sine theta from, this is going to be, oh no, V sine theta. Yeah, sorry. The horizontal velocity is going to be V sine theta. Most sincere apologies. This is the horizontal direction. I was like, why is it becoming 0 all of a sudden? Yes. So this is sine theta. So this is going to be minus cos theta from this point. So that is going to give me a value of 2. Integral 0 to pi d theta, which is essentially the averaging, will give me a factor of pi. Therefore, this quantity here is going to be 2 upon pi v, yes, just v of e. So coming back here, I will continue writing this as W into h by 4 into 2 by pi v of e into m into m, sorry, into m by pi h bar squared. Now this is going to give us, so this h bar squared is h by 2 pi whole square. So this is h square by 4 pi squared. So now let me just write the numerator and denominator fully. This is going to be W times H into M V of E into 4 pi squared into 2 divided by 4 into another pi squared here, yeah, into H squared. So this power gets cancelled, this thing goes, the 4 pi squared cancels out with this 4 pi. You know what? I can do better than this. I can use a different color so that the cuts are more visible. So this cancels out, this cancels out. No, only the power goes out. So essentially what we are left out with is W multiplied by mv of E or 2mv of E by H. Now recall that lambda dB is H by P, which is H by mv. Therefore, I can see that this is the reciprocal of H by mv. So this is equal to 2W by lambda dB, or alternatively, this is equal to W divided by lambda dB by 2. So what does this tell me? Essentially what this tells me is the following. Now I know M of E, or rather M2D of E, is this quantity divided by lambda dB at an energy E by 2. So this implies in a 2D channel, number of modes, or I should say mode density, equals number of half waves or half wavelength of the de Broglie wave associated with the electron. So this de Broglie wave is a matter wave. Let me just finish writing this, then I will explain. The electron, yes. So essentially in quantum mechanics, as you know, the notion of wave-particle duality is often invoked. So what we can say is every particle also exhibits a certain wave property, wave-like property. So if that is the case, then uh, let me consider the number of half wavelengths along, yes, half wavelengths fitting along the width. Yeah, I should also mention this. The channel width. So what does this mean? What this means is the following. If I have a 2D channel, then what determines the number of modes is essentially the number of half wavelengths. So assuming de Broglie wave has a kind of a sine wave like picture, then this is one half length of a sine wave. Like starts from 0, ends at 0. Once it goes through the negative side also, I will get the full wavelength. So this, if the wave associated with an electron flowing through the channel has a wave half wavelength of at least this much, then there will be one mode flowing through the channel. The next level is when we have two wavelengths. So two half wavelengths, that is one full wavelength, which will look something like this. Yeah, just one second. Yeah, and something like this. In this case, there are two modes flowing through. For the next wavelength, there will be three modes available. So this essentially now, this is nothing very phenomenal. Essentially what this is telling is, now lambda dB is of course a measure of the energy. The lower the energy, the higher the, because lower the energy, lower the velocity, therefore the higher the higher the de Broglie wavelength, which implies, wait, am I telling this right? Yes, lower the value of momentum, higher the value of the de Broglie wavelength, therefore fewer modes will be available. Now, as we go higher and higher and higher, more and more and more modes will open in a 2D channel. And that is also kind of observed over here. There is an e to the power half dependence. So as E increases, the mode density also increases with E. Okay, so this gives me the number of modes. So for the case with the green line, we will have two modes. And for the case of the blue line, we will have one mode. So this tells us how the geometry influences the conduction. And this is again something to be expected, because when we were solving quantum mechanics problems, we saw that the boundary conditions determined how the particle behaved. So this is not too different a situation from that. Here also we have a very confined geometry and very particular lengths and widths associated with the channel, and because of that, energies like electrons and all energy values will not participate in conduction. Only certain select energy levels will participate in conduction, and even among those, the number of modes will determine how many electrons at that energy level can actually take part in conduction. Because ultimately you can ask, like one could always ask a question like this, because since this is a dynamic process, many such electrons can move through the channel, because ultimately as it is moving, I can have multiple electrons in the same energy level, because then they will all be at different positions. So all their quantum numbers will not match, and therefore, by Pauli's exclusion principle, or rather, since Pauli's exclusion principle is not violated, I can have multiple electrons flowing through the channel. However, that is not the case. Classically, we will assume that multiple electrons having the same energy can move through the channel. That is why we have the idea of drift velocities and things like that on the macroscopic scale. I shouldn't have said classical. But because of the quantum mechanical nature of conduction here, multiple such electrons cannot pass. The number of electrons that can pass will depend strictly on the energy. Of course, it increases with energy for a 2D channel, and the increase is directly related to the de Broglie wavelength of the associated electron wave. And another thing that can be seen is, as W increases, the mode density also increases commensurately. So as my channel is wider and wider and wider, more and more and more modes will be allowed. As my channel gets narrower and narrower and narrower, the mode density keeps reducing. So this solves, what was this, problem 2. Now let us look at problem 3. So first is derive this expression, like average velocity in the positive x direction for a 1D and a 3D channel. Okay. Again, as before, the velocity is equally distributed uniformly distributed with respect to angle, meaning it depends only on the kinetic energy. There are no angular variations. Although I can have materials where an angular variation will also have some kind of a dependence on the velocity. Right now, we are not assuming that. So in this, the first case is the 1D channel. For a 1D channel, things shouldn't be all that difficult, because if I have just a 1D channel moving from terminal 1 to terminal 2, then the electron can move only in one direction. So it can at a given point, it can either move with Vx in this direction, or it can move in the opposite direction. These are the only allowed Vx directions. It is either with an angle like essentially along the channel or away from the channel. And I want the average velocity along the x-axis. So the average velocity along the x-axis is the total velocity. So in this case, average velocity along the positive x direction at a given energy. If an electron with a certain energy is moving in this direction, its x velocity direction, sorry, its velocity along the x direction is going to be v of e. Nothing more, nothing less. So there wasn't much of a derivation to go on about here. Now look at the second case, which is the 3D channel. Now for a 3D, not channel, why not? Channel. Now for a 3D system, yeah, I need to draw a little bit more. I will have two angular directions. Essentially, there can be two angular, like two angles that I can measure in a 2D channel. Why is this so hard? Essentially, this, yeah. Yes. So if I have an electron entering here, let me say this line joining these 2 points is my x-axis. Well, technically, if we are being geometrically accurate, this should be the z-axis, but it doesn't matter. I can just say x direction is the direction of the uh, conduction. Any electron entering the material will make an angle with this axis, and its projection will make an angle, its projection on the plane will also make an angle over here. So I'm going to have a theta and a phi. So this is my phi and this is going to be my theta. So of course Vx is going to be V of E. So now I'm measuring this angle from the axis itself, cos theta. Now one should remember that in this convention, theta can vary from 0 to pi by 2. At 0, it will be fully along one of these faces, and at pi by 2, it is going to be completely along this axis of conduction. So, yeah, I should not have drawn these blue lines. That is making this diagram look very cluttered. Never mind. I hope all of you know what spherical polar coordinates are. And phi can, of course, vary from theta belongs to this region, and phi can of course vary in all 360 degrees. So 0 to 2 pi. However, what one should remember is when I'm integrating this, I should look for a single volume element. So because here it was quite simple, it was just d theta. But here that is no longer the case when we are looking at uh, the 2D coordinates, 3D coordinates. So in that case, what we will have to do is the following, wherein average Vx plus, so I should write this as Vx plus of E is going to be integral V of E cos theta sin theta d theta d phi. So this is the volume element in the spherical polar coordinates, where of course this will be a double integral with one limit going from 0 to pi by 2 and the other going from 0 to 2 pi, and in the denominator we'll have the same double integral. Remember, like it's not d theta phi, it's d theta d phi. Remember that in multiple integrals, the first integral limits applies to the first integration variable and the second applies to the outer integration variable. That is the order in which we go. So this is going to be just sine theta d theta d phi. Cos theta sin theta can be written as sine 2 theta by 2. Oh, not cos, sine 2 theta by 2. Apologies. Sine 2 theta by 2. So this is going to be 1 by 2 into integral 0 to 2 pi 0 to pi by 2 sine 2 theta d theta d phi. Now, and so the denominator we can already integrate. This quantity is like sin theta d theta from 0 to 2 pi is going to be minus cos theta subtracted between 0 and pi. So that is going to give me 1, and d phi is going to be 2 pi. So the denominator is 2 pi. Now over here I can say t is equal to 2 theta, which implies dt is 2 d theta, which implies of course d theta is dt by 2. Now the 1 by 2 factor can be reabsorbed into the integral. So this is integral 0 to 2 pi. I should have done the d phi integral first, but it's fine. 0 to pi sin t dt d phi divided by 2 pi. Now, wait, am I doing this correctly? So sin theta, and then this is going to be 1 over half 0 to pi. So this is going to give me a factor of 2. Yes. So the integral over here is going to give us a factor of 2, and then there is going to be a factor of 2 pi. So from the, wait, have I made a mistake here? Because it cannot be greater than v of e. I need to get some other factor of t. So that will vary from 0 to pi. D theta is dt. Oh my god, yes. D theta is dt by 2. The factor of half will not be reabsorbed. I am so sorry. Yes, that makes all the difference. So which is further equal to, so there is going to be dt by 2 over here. Yes. So this integral sin t dt from 0 to pi is 2. The 2 and 2 will cancel out. I will have 1 by 2. And then the 2 pi and 2 pi will also cancel out. I should have written v of e over here. And I will write v of e over here. And as you can see, everything cancels out perfectly well. And we will finally have a rather familiar looking result. A is equal to v of e by 2, which is more or less what we expect, because I have a 3D volume, electron can move leftwards or rightwards. It has only two possible directions. So if I'm evaluating the average velocity of the electron moving on the right side, it is going to be half of the total velocity, statistically speaking. And that is what we derive here. Okay, so that is this problem done. Yes, now we come to the final topic of the day. Yeah, today's session turns out is going to be somewhat shorter than the previous weeks, but that is perfectly fine. So now, what about the diffusive limit? What is the diffusive limit? So for that, a brief recap of diffusive conduction. When we consider conduction in bulk materials, what we essentially do is we consider the following. We will take a small like slice over here, and then we will say there is a charge density rho of x, and then there is a charge density, this length is delta x, and then I will have rho of x plus delta x, and we will essentially say I is equal to some dm diffusion constant minus rho of x minus rho of x plus delta x divided by delta x, where rho is the charge density. And this is how we conventionally solve for current conduction in macroscopic current values. We will say that electron flow is from a region of higher concentration to lower concentration. Current is going to be in the reverse direction. That is why I have the minus sign, and dn is the diffusion constant. So now why is this happening? This can be understood through the statistical motion of electrons. If I have more electrons on one side of a particular strip when compared to the other side, then just statistical collisions. When electrons move across this barrier to a region of lower density, there are very few electrons there to scatter them back. So since backscattering reduces, I can say more electrons move towards the region of lower density. So I can do this, like take different slices and look at how many electrons are passing through each slice. Of course, this is going to be not just I. This should technically be the current density J, but that doesn't matter. I will just write it as I for now. Don't have to be all that accurate because we are currently not deriving this. Whatever is in red, just an overview. Now, the ballistic model is valid if and only if the channel length is very, very small, like very small, compared to the mean free path of the electrons. So mean free path is the average distance the electron travels without undergoing collisions. And that is the primary reason we were able to make the assumption of ballistic conduction in the case of nanoscale channels, because the channel length is so small. However, when the channel length is comparable to or greater than the mean free path of the electron, which I shall denote as lambda e, then the number of modes gets reduced by a factor known as the transmission coefficient, which is given by lambda of e divided by lambda of e plus L. Now you can ask what this is. It's actually not, hard to imagine. Like if my channel length is L, okay, let me say. Essentially, the idea is for every lambda e, let me, so lambda of e is the mean free path. Which implies average number of collisions is equal to L divided by lambda of e. This is the average number of collisions. Therefore, the probability of a collision will be the inverse of this. Lambda of e by L. So this is the probability of a collision occurring. Okay, is the number of collisions over. So there should be probability of collisions uh, per what? Per unit length essentially. Yes, per unit length. So as my length increases, as the length of my channel increases, the quantity that I will have to look for is lambda of e. You know what? We don't need this one. We can just look at this. I will bring this up later. Right now, it is not needed. I jumped ahead a few points. Yeah. So the average number of collisions is L by lambda e. Oh yeah, of course I need that. So the reciprocal of this gives us the average number of collisions n, which implies probability of collisions per unit time. I shouldn't say probability of collisions, I should say rate of collisions. Yes, that will make sense. So rate of collisions, because this length is the length of the channel. So in the time that it takes to cross the channel, it will undergo lambda of E upon L collisions. So this gives me the rate of collisions, which implies if these many collisions are occurring, then those many times ballistic transport gets hindered. So that essentially gives us this measure. Now, why do I have a lambda of E plus L? The idea is, irrespective of how my channel is, the electron will undergo scattering, will undergo energy loss and collision when it is hitting the edge of the channel. So even if it is a ballistic channel, there is going to be a final scattering as it reaches the second electrode. So that is why the total length travel should be considered as lambda of E plus L, because even in a nanoscale device, like there is guaranteed to be at least one collision. So because of that, we have this plus one quantity here. So number of collisions is going to be 1 plus this, which will give me a transmission coefficient that is going to be, or rather, uh, it's lambda e plus this, sorry, yes. So that will give me this quantity, the transmission coefficient, which essentially gives me the average, like, yeah, what's given here, this is going to give me the rate of collisions, the probability of collisions while the electron is present in a long channel. So whenever a collision occurs, that mode kind of vanishes, like that mode is no longer considered for ballistic conduction. So the higher the rate of collisions, the lower the number of modes I will end up having. So you'll see what that looks like. So this is, I think, the last numerical, yes, for today. Let us say for some energy, the transmission coefficient T of E is given to be 0.8. Okay. Now, the question that is asked is, what will happen to a transmission to the transmission coefficient when the length of the same channel is increased to 10 times the initial value? So what does this tell me? This tells me lambda V divided by lambda V plus L is equal to 0.8. So from this, I can rearrange and write lambda V is equal to 0.8 L plus, or rather lambda V plus, sorry, L. So this further implies L is equal to 0.2 by 0.8 lambda V. So over here, yes, so this is going to be 1 by 4 times lambda V. Observe that even when the channel length is 1/4 of the, so for, I should write this here, T of E is equal to 1 for fully ballistic transport. However, as you can see here, even when the channel length is 1/4 of the mean free path, I'm not getting transmission coefficient equal to 1. So what we need to understand is that essentially for this quantity to be 1, L should almost tend to 0. It should be very small compared to lambda of E. It shouldn't, like, even being close to lambda of E is not acceptable, because even there is a non-zero probability for collisions to occur. So my channel length needs to be so small when compared to the mean free path of the electrons that I can effectively neglect that parameter while calculating the uh, uh, transmission coefficient. So this gives me the relation between L and lambda E. So this is, let me say, the first part. Now the second part is L goes to 10 times L, which implies the new length L prime is equal to 10 times 10 into this, so that is going to be 2.5 lambda of E. Therefore, yeah, I will leave it at this. So 2.5 times lambda of E. I will just underline this to make sure that people can read this. People don't forget to read this when they go through the answers. So that implies the new transmission coefficient T dash of E is going to be lambda of E divided by lambda plus 2.5. This is 5 by 2. So 5 by 2 plus 1 is going to give me 7 by 2. So this is going to be 2 by 7. 2 by 7 is 0.28, so on, approximately 0.3. So as you can see, increasing it by 10 times reduces by the transmission coefficient by less than, like it reduces by a factor of more than 2. From 0.8, the transmission coefficient went down to 0.3. As an added example, if I consider L goes to 100 times L dash is equal to 25 lambda of E, then what we will have is T of E or T double dash of E is going to be 1 by 26, because it's going to be lambda of E divided by lambda of E plus 25 times lambda of E. So that's 1 by 26. And this will be approximately how much? So 1 by 26, it's essentially going to be, just 1 second, let me verify this to give a more accurate answer. Yeah, so this will come out to be, of course, 0.038, which is approximately 0.04. So previously, I can say how many ever modes I had. Wait. Previously, how many ever modes I had? 80% of the modes are ballistic. That's essentially what the transmission coefficient means. At this energy level, 80% of the modes are available for ballistic transmission. Uh, Over here, it tells me only 30% are available. And over here, so this corresponds to 30%. And over here, we are all the way down to 4%. And any more than this, the number is going to fall. We can see that how. As an example, let me say M of E. Remember, M of E does not depend on the length of the channel. M of E is just dependent on the geometry of the channel, because the length dependence has been all but removed over here, because this is per unit volume or unit area, and gamma of E is just an energy broadening. So this is not concerned with the dimensionality of the channel. Once we invoke the dimensionality, we will need the transmission coefficient to be included in the expression. So if I say M of E at that same energy level is say 20, then at our initial length, T is equal to 0.8, will tell me that there are 16 channels, 16 modes available at this energy. Now T of E is equal to 0.3 would tell me there are only 6 modes available. and T dash of E. I have T double dash of E, which is equal to 0.04, 4%. So 5%, like 10% of 20 is 2. 5% is 1. 5% is 1, half of that. 4% is less than that. So we will have 0.8 modes, which we do not consider. Number of modes always has to be greater than 1. Because even in a 2D case, we can see that at least one half wavelength of the de Broglie, like one half de Broglie wavelength should fit within the width of my channel. If that is not happening, if the energy level is further lower than that, then conduction is not, like those modes are not going to participate in the conduction. So, which is equivalent to saying 0 modes. So, if I have a channel of this length, does that mean the material stops conducting by just increasing the length? The answer is no. At this point, the only thing we can say is only diffusive transport occurs. Essentially, I can no longer ensure that there is a ballistic transport in my material. In fact, I can guarantee that there is no ballistic current, only diffusive current. So these are some, basic numericals and basic concepts that we have looked at in today's session. So the idea of modes has been introduced. We have given some physical picture also here for intuition, and then we have seen what impact the Fermi level has on these things or the Fermi distribution has on these things. We've started with a basic expression for the de Broglie, the mode density in a 2D channel and worked through its dependence on the de Broglie wavelength. And then we have seen how to calculate the average velocity in the positive x direction. And we have finally finished today's discussion by going through a brief problem on the transmission coefficient, which gives us the extent of ballistic transport in these ballistic ratio of ballistic and diffusive conduction that is present in a channel. So not tomorrow's, next week's discussion, we'll kind of begin from this point. So this is going to be the starting point for our discussion. And we will see further how these things are developed, how to derive the conductivity for the channel at different conductance of the channel at different bias conditions. And then we shall see what happens when things extend to the full diffusive limit. How does the behavior look like? Does it give us familiar results or what happens? So those are the kind of things that we shall be looking at in next week's session. So with this, I will bring today's session to a close. I thank you all for joining and for those who shall be listening to it later, for listening. So yeah, I'll see you all again, same time next week. Thank you very much. So I will stop the recording now.